we saw the Johnson's algorithm, which could provide an optimum solution to a n job 2 machine flow shop sequencing problem to minimize make span. We also showed a numerical illustration to explain the various steps in the Johnson's algorithm. Now the next obvious question is, can the Johnson's algorithm work for a 3 machine problem? Other things being equal, n jobs, 3 machines, flow shop sequencing problem to minimize make span. Now Johnson actually proved that under certain conditions the Johnson's algorithm can be extended to solve the 3 machine problem optimally. So Johnson gave 2 conditions, which are this: if maximum of the processing times is less than or equal to minimum of the processing time, or less than or equal to minimum of the. Now this condition says that the maximum of the processing times of the jobs on machine number 2, which is here, the maximum of the processing times. Now we are considering a 4 job 3 machine problem, flow shop sequencing problem to minimize make span. So the largest of the values for machine 2, which is 10, should be less than or equal to the smallest of the values on machine 3, which happens to be another 10. So 10, or the largest on machine 2, which is 10, should be less than or equal to the smallest on machine 1, which is 3. Now out of the 2 inequalities, we observe that for this particular problem, the first one is satisfied, the second one is not satisfied, but it is also enough if one of them is satisfied. Therefore the Johnson condition holds for this problem. So when the Johnson condition holds for this problem, how do we get the optimum solution? What we do here is we create an equivalent 2 machine problem, because the basic Johnson's algorithm works for 2 machines. So we create an equivalent 2 machine problem with the 4 jobs J1, J2, J3 and J4 on 2 equivalent machines, and these 2 equivalent machines are called M1 plus M2 and M2 plus M3. So the first column here, which is called M1 plus M2, is actually the sum of the processing times on machines 1 and 2. So it becomes 3 plus 8 11, 12 plus 9 21, 8 plus 6 14 and 12 plus 10 22. Second column of the equivalent Johnson 2 machine problem is M2 plus M3, which means we add the processing times on machines 2 and 3 to get 8 plus 10 18, 9 plus 12 21, 13 plus 6 19 and 10 plus 16 26. Now we have an equivalent Johnson problem with 2 machines. So we apply the Johnson's algorithm on this data and try and get the optimum sequence that minimizes make span for the equivalent 2 machine problem. So once again, as we have done in the past, we write a small table with 4 positions which are for the 4 jobs. Take the smallest number available in this, which happens to be 11, and it happens for job 1. Therefore it happens to be for job 1 on this first machine. So come from the left hand side and place job 1 in the first available position. Now strike off job 1. Now try to find out the smallest number that is available, which is 14 here, which is for job 3, and on the first equivalent machine. So, come from the left and put J3 here. Now, once again remove this. Now, find out the smallest number, which happens to be 21, which is for J2, both on M1 and M2. So, there is a tie. So, let us go by this 21, which happens to be on the first machine. Therefore, J2 will come here, which automatically means that the leftover job J4 will come to this side. Now, since there was a tie, the tie could be broken other way. So, when we break the tie the other way, the sequence would have been J1, J3. Choosing this 21 would have put J2 here and J4 here. Now, for both these sequences, let us try and find out the make span with the original data, because the original data is the problem that we are looking at. So, we look at the sequence J1, J3, J2, J4. And we look only at completion times on M1, M2, M3, J1, J3, J2 and J4. So, J1 goes first, comes out of machine 1 at time equal to 3, requires 3 minutes. At time equal to 3, it goes to machine 2, it requires a further 8 minutes processing. So, comes out at time equal to 11. Once again enters M3 at 11 and comes out at 21, because it requires a further 10 minutes on M3. J3 on M1, J3 starts at time equal to 3, requires another 8, so 3 plus 8, 11. Exactly at 11 M2 is free, so it takes another 6 units, 11 plus 6, 17. Now it has come out of M2, but M3 is free only at time equal to 21, therefore it visits M3 at time equal to 21 and requires another 13 time units, so 21 plus 13 is 34. Now J2 starts at time equal to 11, finishes at time equal to 23. Now at time equal to 23, M2 is available, so requires another 9 units on M2, so 23 plus 9, 32, but has to wait for M3 because M3 is available at 34. So 34 plus 13, 34 plus 12 is 46. Now J4 enters, so M1 is available at time equal to 23, so J4 requires another 12 units, so 23 plus 12, 35. At 35 M2 is free, it requires another 10 time units, so finishes at 45. Now it has to wait for M3 because M3 is available only at 46. So enters or visits M3 at 46, takes another 16 time units and comes out at time equal to 62. So the make span for this sequence will be 62, we have here. We also have an alternate sequence which is J1, J3, J4 and J2. So let us try and compute the make span for the other sequence J1, J3, J4 and J2. So J1, J3, J4 and J2. Since J1 and J3 are the first two jobs, the completion times will be the same up to this. So we can write 3, 11, 21, 11, 17, 34. So J4 enters at time equal to 11 on M1 and finishes at 23. Now at 23 M2 is available, so takes another 10 units, so finishes at 33. and has to wait till 34 because M3 is available only at 34. So visits M3 at 34 requires another 16 units. So 34 plus 16 is 50, comes out at 50. Now J2 enters M1 at time equal to 23. So 23 plus 12, 35 it comes out. So at 35 M2 is available. So plus takes another 9 units, 35 plus 9 is 44, but has to wait till 50. So at 50 it visits M3, takes another 12 units and comes out at time equal to 62. So once again the make span for the second sequence is also 62. So there are two alternate solutions, both of which are optimum with the same make span of 62. So this is how the Johnson's algorithm for the 2 machine problem can be extended to a 3 machine case, provided the data satisfies these conditions. So obviously the next question that would come is, what happens if this data does not satisfy the condition? Is there another way to try and get to the optimum solution? Now what happens is, the moment we do not satisfy this condition, then we realize that the Johnson's extension does not give the optimum solution to the problem or optimum make span to the problem. So we have to resort to, if we really want to find the optimum, then we have to resort to what are called the branch and bound algorithms, which are computationally a little more demanding, but nevertheless give us optimum solution to the problem. So we will look at another illustration through which we explain the branch and bound algorithm to minimize the make span on multiple processors in a flow shop. Now let us consider this numerical example and try and see whether first it satisfies the Johnson's condition, and if so use it, if not try and look at a branch and bound algorithm to solve. Now the Johnson condition says maximum processing time on machine 2, which happens to be 98, should be less than or equal to the minimum of this. So minimum of this happens to be 1, minimum on this happens to be 8. So the Johnson condition is clearly not satisfied. So we cannot apply this to try and get the optimum solution or the optimum make span to the problem. Now let us ask ourselves a few more questions. Now by looking at this data, can we try and estimate the make span? Try and have what is called a lower estimate to the make span or a lower bound to the make span. Now what is the lower bound to the make span? Now let us add the processing times on M1, M2 and M3. So this is 10. So this is 200 if we add on M1, on M2 is 237 on M2 and 129 on M3. So sum of processing times on 3 machines are 200, 237 and 129. Now the maximum of these 3 is 237, and we could say definitely that the make span cannot be smaller than 237, because all the jobs have to go through machine 2 and the total workload on machine 2 itself is 237. Therefore, the make span can only be more than, greater than or equal to 237. So, the maximum of the sum of processing times on the machines give us a lower bound to the make span. So, we could say lower bound is 237. Now, we can actually make this lower bound slightly better, or we can tighten the lower bound. How do we do that? Now, if we take the first machine, now the total load or total processing on the first machine itself is 200, but then all the jobs are completed only when the last job entering machine 1 also finishes on machine 2 and also finishes on machine 3. So, the machine 1 alone would require 200. So, there will be an additional thing that will go into the make span, because the last of the jobs entering M1 has to finish M2 and M3. So, the minimum possible increase after this 200 is the minimum of the sum of processing times on M2 plus M3. So, now we realize that this is 11 plus 82 is 93, this is 92 plus 8 is 100, this is 66, this is 107. So, the minimum increase that will happen has to be 66, because one of these 4 jobs has to be the last job on the machine, and if job 1 happens to be the last job, then there is an additional 93. If job 2 happens to be the last job, there is an additional 100. If job 3 happens to be the last job, there is an additional 66. Job 4 happens to be the last, there is an additional 107. So, definitely the make span will go up by 66. So, the make span, now the lower bound on the make span is 200 plus 66, which is sigma Pi1, sum of the processing times on machine 1, plus minimum over I, minimum over the jobs Pi2 plus Pi3, sum of processing times on machines 2 and machine 3. So, this becomes 266. So, one could say that the make span has to be 266 or more. Now, this is the lower bound that is computed based on machine 1. Now, let us compute a lower bound based on machine 2. Now, machine 2 by itself has a load of 237, but the first job entering the flow shop cannot start processing on machine 2 unless it has finished machine 1. So, the earliest time machine 2 can begin is the minimum of these numbers. So, the earliest machine 2 can begin is 1. So, lower bound is again 1, which is the earliest machine 2 can begin, plus machine 2 requires at least 237 time units. So, earliest machine 2 can finish everything is 1 plus 237, and it is still not over, because the last job on machine 2 has to visit machine 3. So, there is an additional component with the last job on machine 2 visiting machine 3, and therefore, at least a minimum of another 8 will have to be incurred on machine 3 before all the jobs are completed. So, 1 plus 237 plus 8, which is 246. So, to write this algebraically, we will say minimum over I, minimum over jobs Pi1 plus sigma Pi2 plus minimum over I Pi3 is another lower estimate of the make span. So, the make span cannot be more than, make span cannot be less than 246, it has to be 246 or more. Now, lower bound based on machine 3, let us call these as LB1, LB2 and LB3. Lower bound based on machine 3 is this. Machine 3 by itself has a time of 129, but machine 3 cannot begin till at least one job has finished on M1 and M2. So, the earliest machine 3 can begin is the minimum of the sum of these two. So, this is 88, this is 126, this is 124 and this is 99. So, minimum the earliest M3 can begin is 88 if J1 happens to be the first job. So, earliest it can begin is 88 and it requires at least 129, then the last job is over. So, the earliest based on M3 would be 88 plus 129. So, 137, 129, 137, 217. Now, to write it in our notation, this will be minimum over I Pi1 plus Pi2 plus sigma Pi3 over I. So, now we have calculated 3 lower bounds, one based on each machine. So, based on M1 we could say that 266 is the lower bound to the makespan, based on M2 246 and based on M3 217. Now, out of the 3 we could say now that the makespan can only be 246 or more. So, the actual lower bound is the maximum of the 3 lower bounds that we have, and then we say that the lower bound right now is 266 for the makespan is 266, which is the biggest of the 3 numbers. So, we start what is called the branch and bound tree by saying that the lower bound is 266. Now, what we do is we try and branch in this tree by trying to fix each of the jobs as the first job in the sequence. So, there are 4 jobs, so there are 4 possible branches. The 4 possible branches will have J1 or job 1 as the first job, job 2 as the second, job 3 as the third, I am sorry, 4 jobs J1, J2, J3, J4 each as first job in the sequence. So, this sequence will have J1 as the first job, this sequence will have J2 as the first job and so on. So, now we try and find out the lower bound for each of these 4 nodes of the branch and bound tree. So, let us first compute this. So, for this we actually compute 3 numbers once again based on these 3 things, which means that if we fix J1 as the first job, then on M1 all the processing will be over at time equal to 200, and this lower bound will take the minimum of Pi2 plus Pi3 over I. Since J1 is the first job, J1 cannot be the last job, because the very basic idea of this lower bound is that the total processing time on M1 plus the last job's processing time on M2 plus M3. So, since J1 is fixed as the first job, J1 cannot be the last job. Therefore, to compute this minimum, we would only look at the minimum of this, this and this. We will leave out this 93. So, minimum of this still remains as 66. So, 200 plus 66 is the first computation. Now, for the second computation, J1 is the first job. So, J1 takes 77 time units on machine 1. So, M2 can start only at time equal to 77. So, this will become 77 plus sum of processing times on machine 2, which is 237, plus the last on M3 we will leave out J1 because J1 is already the first job. So, J1 cannot be the last job. So, the last job can be only J2 or J3 or J4. So, out of J2 or J3 or J4 we take the minimum. So, out of 8, 30 and 39 we take the minimum, which again happens to be 8. So, 77 plus 237 plus 8. Now, on M3 J1 is the first job. So, earliest this can begin is 77 plus 11, which is 88, and M3 by itself has a time of 129. So, the maximum of these three numbers will now be the lower bound if job 1 is fixed as the first job, and we calculate that. So, this is 266, this is 312, 237, 245, 252, 322. So, this is 322, and this will be 217. So, the maximum of the three values is 322, therefore, we say that if we start with J1, the lower bound is 322. Now, let us do these computations with J2 as the first job. Now, when J2 is the first job, on M1 the total time required is 200. Now, J2 cannot be the last job because it is the first job. So, the last job can only be J1 or J3 or J4. So, the minimum is 93, again 66 and 107. So, this will remain as 200 plus 66. Now, the lower bound based on M2, J2 is the first job. So, earliest M2 can begin is 34 plus 237, which is the sum of processing times on this. So, 34 plus 237 . Since J2 is the first job, now it cannot be the last job. So, the last job can only be 1, 3 or 4. So, take the minimum of 1, 3 or 4, which happens to be 9. So, we have plus another 9. Now, if J2 happens to be the first job, the earliest M3 can begin is the sum of 34 plus 92, which is 126 plus another 129. So, 126 plus 129. So, this is 266, this is 237 plus 9 is 246, 250, 280, this is 126 plus 129 is 255. So, maximum of the 3 is 280, and therefore, 280 is the lower bound when J2 is fixed as the first job. So, let us now do that if J3 is fixed as the first job. Now, when J3 is fixed as the first job, M1 by itself will require 200. The last of the jobs cannot be J3 because J3 is fixed as the first job. So, the last can only be J1, J2 or J4. So, sum of 11 plus 82, 93, 92 plus 8, 100, 98 plus 9, 107. So, minimum is 93 here. So, we will get 200 plus 93. Now, if J3 happens to be the first job, the earliest M2 can begin is 88 because J3 has to finish on M1 and only then it can enter M2. So, earliest it can enter is 88 plus another 237. Now, J3 cannot be the last job. So, we have to take the minimum of this, this and this, which happens to be 8. So, 88 plus 237 plus 8. So, 88 plus 237 plus 8. Now, once again, if J3 is the first job, M3 earliest M3 can begin is after it has finished this and this, which is 88 plus 36, 124 plus another 129. So, 124 plus 129, this is 293, this is 245, 253, 333, and this is 253. So, the highest of them is 333. So, the lower bound becomes 333. Now let us look at J4 as the first job and complete this. So M1 takes a time equal to 200, J4 now cannot be the last job can only be J1, J2 and J3. So minimum of 93, 100 and 66. So you will get the same 200 plus 66 here. Now if J4 is the first job, the earliest M2 can begin is 1. So 1 plus 237 is 238. Once again J4 cannot be the last job, so minimum of this and this, which is 8. So 1 plus 237 plus 8, which is 246. 1 plus 237 plus 8, which is 246. And if J4 is the first job, earliest M3 can begin is 99, because J4 has to finish 1 plus 98. So 99 plus another 129, which is 226. 99 plus 129, which is 228. So this is 266, this is 246, this is 228. So lower bound remains as 266. So what we have observed now after this calculation is that if we fix job J1 as the first job, the make span is going to be 322 or more. If we fix J2, the make span is going to be 280 or more. If we fix J3, 333 or more, and if we fix J4, it is 266 or more. Since we want to minimize the make span, we proceed in this direction, because this is the smallest number, 266. So there is a possibility that we get a smaller number as we proceed from here. So we proceed from this node right now. We still have to evaluate this and this, we will see that as we move along, but then we proceed from the node which has the smallest value of the lower bound. So from this node we proceed. Now we have already fixed job 4 as the first job. So we have to now fix the second job. So job 1 is the second job, job 2 can be the second job, job 3 can be the second job. Now let us evaluate this. If job 4 is the first job and job 1 is the second job. Now what we have to do is, now we have what is called a partial sequence. So according to this, the partial sequence is J4 and then J1. Now let us first evaluate the completion times for this partial sequence, which is J4 and J1. Let us first evaluate the completion times on this. So J4 begins here. So J4, this is completion time. So J4 is 1, it finishes at 1. 1 plus 98, 99, and 99 plus 9 is 108. Now J1 is here, so J1 starts at 1 and finishes at 78. Now we are evaluating this for the partial sequence J4, J1. Now at 99 it visits M2, takes another 11 units, so comes out at 110. So at 110 M3 is free, takes another 82 units, comes out at 192. So we keep this partial sequence with us to help us make the lower bound better. Now what do? Now we have to find out the 3 lower bound corresponding to the 3 machines. So corresponding to M1, the minimum time is 200. Already 4 and 1 are fixed, 2 and 3 are remaining. So 2 and 3, one of them only can be the last job. So we take the minimum of 166. So the first lower bound still remains as 200 plus 66. Now when we look at M2, the computation will be very interesting. So we would have, now at this point when we consider the partial sequence J4 J1, now M2 is available for the remaining two jobs which are J2 and J3 at time equal to 110. So, the minimum M2 can complete all the jobs is 110 plus 92 plus 36. So, 110 plus 92 plus 36 is 110 plus 92 is 202, 202 plus 36 is 238. Now, the earliest M2 can complete is 238. Now, two jobs are remaining J2 and J3, one of them has to be the last job. So, it would require an additional 8 which is the minimum of this. So, 238 plus 8. Now, we will see the same thing happening for M3 also. Now, based on this partial sequence, M3 is available for the remaining jobs J2 and J3 at time equal to 192. So, at time equal to 192, M3 can start looking at J2 and J3. So, now from 192, J2 and J3 plus 8 200 plus 30 230. So, 192 plus 8 plus 30 230. So, the lower bound is 266, 246, 230. So, lower bound remains as 266. Now, let us show one more computation here with J4 and J2 as the two jobs. So, we will do for J4 and J2. Now, let us quickly do the completion times. So, J4 will be again 199 and 108 coming from this 199 and 108. Now, J2 enters at 1, finishes at 35. So, J2 finishes at 35, enters at 99, requires another 92. So, 99 plus 92 is 191. So, this is 191 and M3 is free at 191, takes another 8 units. So, 199 it comes out. Now, using this partial sequence, we will now go back and try and find out the lower bounds. So, as far as M1 is concerned, M1 will finish at 200, jobs 4 and 2 are fixed. So, 1 and 3 are available. So, 1 and 3, once again 3 is the minimum with 66. So, the first lower bound will be 200 plus 66. Now, M2 is available at 191 for jobs 1 and 3. So, 191 plus 1 and 3, 191, 192, 202, 238. So, at 238 all the jobs can be over earliest in M2, then once again it has to go for another minimum over 1 and 3 which is another 30. So, this will be 191 plus sum of processing times of 1 and 3 which is 11 plus 36 which is 47 plus 30. Now, as far as M3 is concerned, M3 is available at 199 to do 1 and 3. So, 199 plus 82 plus 30 which is 112. So, 199 plus 112. Now, this is 266. Now, this is 191 plus 30 is 221, 228, 268 and this is 199 plus 112, 199 plus 112, 211 plus 100 is 311. So, the lower bound becomes 311 when we do this. Now, let us calculate the other lower bound for J4 and J3 also. Now, to do that we have J4 and J3 here. So, we will quickly do the completion times. 199 and 108. For J3 it is 88, so 1 plus 88 is 89, starts at 99, requires another 36, so 135, 99 plus 36. At 135 M3 is free, so takes another 30, 135 plus 30 is 165. So again based on the lower bounds, so as far as M1 is concerned it will take 200. Now 4 and 3 are already fixed, so 1 and 2 are available. So minimum over, this is 93, this is 100. So 200 plus 93, which is 293. So 200 plus 93 is equal to 293. The earliest M2 is available is 135 for 1 and 2. So 135 plus this is the earliest M2 is over. Then the last job has to do one more operation. So minimum over 82 and 8, which is 8. So 132 plus 11 plus 92 plus 8, 135 plus 11 plus 92 plus 8. And M3 is available at 165 for 1 and 2, so it has to do these two plus another 90. So 165 plus 90, 255, this is 293. So this is 100, 235, 246, so the lower bound remains at 293. So now we have all these, then we still need to proceed to get to the solution. So now the smallest available number is still 266. So we can proceed from this to try and get some more solutions. So we have already fixed 2 positions, so we could fix the third position now. So J4 and J1 have been fixed, so now J2 and J3 are remaining. So we will say we fix J2 as the third job, we fix J3 as the third job in the other sequence. So we fix 3 positions now, so J4, J1 and J2. So we can continue in the same way to get the lower bound for J4, J1 and J2, but we observe that there are only 4 jobs, we have already fixed 3 positions. So the leftover job has to automatically take the 4th position. So instead of computing a lower bound, we compute the make span for a full sequence, which is J4, J1, J2 and J3. So J4, J1, J2 and J3 is the other alternate sequence is J4, J1, J3 and J2. So the other alternate sequence is J4, J3, J4, J1, J3 and J2, because here we fix J3 as the third job, so the leftover job, which is J2, will be the 4th job. So branching from here we are able to get 2 full sequences, because in all these partial sequence there is only one more job to go. So we can evaluate this sequence or we can evaluate this sequence, we can evaluate either of them. So let us first evaluate this sequence and try to learn a few things, then we will come back to this sequence. So we evaluate the full sequence here, we already have for J4 and J1. So for J4 and J1 we already have here, so we write 199, 108, 78, 110 and 192. Now we look at J3. Now J3 enters at 78, takes another 88, so 86, 166. So at 166 M2 is free, so it takes another 36, 166, 172, 202. At 202 again M3 is free, takes another 30, so 232. Now J2 enters at 166 plus 34 is 200, waits till 202 for M2, takes another 92, so 202 plus 92 is 294. So at 294 M3 is free, so goes to M3 and comes out at 302. Now 302 is the make span associated with this sequence. Now we have a feasible solution with make span equal to 302. 4132 is a valid sequence. It is one out of the 4 factorial possible sequences for this problem. So it is feasible and has a make span of 302. So the moment we have a feasible solution with a make span of 302, we also understand that the optimum now can be 302 or less. So the feasible solution provides an upper bound to the optimum. So it provides an upper bound to the optimum, and therefore the optimum now is 302 or less. Now with this additional information, we now observe that if we look at this node from here, with fixing J1 as the first job, we understand from here that if we proceed down, the make span that we will get can only be greater than or equal to 322. So we are now not interested in any solution which has make span 302 or more, because we want to minimize the make span, and we already have a solution with 302. So there is no need for us now to proceed from here, because we are only going to get solutions which are poorer than 302. So we decide not to proceed from this. So we say that we fathom this node. So this node is fathomed because the lower bound here is greater than or equal to the current best upper bound of 302. So 302 acts as an upper bound. So we fathom a node when the lower bound in that node is greater than or equal to current best upper bound. Now similarly, the 333 is also fathomed for the same reason that lower bound is greater than or equal to the current best upper bound. But we can't do that to this 280. Now this 311 can also be fathomed. We normally use fathom or with an F, they mean the same. So we could put an F and say that it is fathomed for the same reason that the lower bound is bigger than the current best upper bound. We can't proceed from here because we have already reached the full sequence. So this node is fathomed by upper bound or by feasibility, because we have a feasible solution there, we cannot proceed anymore. So now we realize that doing this computation has helped us actually indirectly, because we now do not have to proceed and evaluate sequences from here, we do not have to proceed from here, we do not have to proceed from here. But there are still some nodes that are active, which means we can move from here, we can move from this 293, we can evaluate this. So we now try and evaluate this. So we already know the sequence for J4, J1, so you get 1, 99, 108, 78, 110 and 192. Now J2 enters at 78, takes another 34, so 112 is when J2 finishes here. At 112 machine 2 is available at 110 itself, so takes another 92 units. So 112 plus 92 is 204. At 204 M3 is available, takes another 8 units. So at 212 this leaves. Now J3 is the last job. J3 enters M1 at 112. 112 plus 88 is 200. Waits till 204 and then visits M2 at 204. Requires another 36 time units. 204 plus 36 is 240. M3 is available at 240, so visits M3, takes another 30 units and comes out at 270. So now the make span associated with this sequence is 270. Now this 270 is going to help us in many ways. Now this node, as I said, is fathomed by feasibility. this 270 is an upper bound, and the moment we have a solution with make span equal to 270, it is better than the current best solution of 302. So, we update. So, we keep the best solution now as 270. Now, the moment we have 270 solution, we are not interested in any solutions which are more than 270. So, we now start looking at all these nodes. Now, this tells us that if we move in from this direction, it is going to be 280 or more. So, we do not have to move from here because we already have a solution of 270. So, this is again fathomed with lower bound greater than or equal to upper bound. The only difference is that the upper bound has been updated. So, from 302 it has become 270, therefore, you can fathom this. Now, proceeding here, which is the one that is available, 293 can also be fathomed with lower bound greater than upper bound. So, now we realize that there is no active node in this network. So, we cannot proceed any more from this network because all the nodes have been fathomed. They have been fathomed either because they give a feasible solution, or they have been fathomed because the lower bound associated with that node is greater than or equal to the current best upper bound. So, there is no more node to proceed, the algorithm terminates, the branch and bound algorithm terminates, and the best feasible solution at this point, which is the solution with 270, is the optimum solution. So, the optimum solution is J4, J1, J2, J3 with 270 as the optimum make span. So, this is how the branch and bound algorithm works. So, we branch by creating sequences and partial sequences, we evaluate lower bounds, and then as we move down the tree we evaluate feasible solutions and upper bounds and try to fathom the nodes based on two things, in this case based on a feasible solution and based on the condition that lower bound is greater than upper bound. Now, this is like an implicit enumeration algorithm. We have actually evaluated all the 4 factorial, but not explicitly. We have explicitly evaluated only 2 out of the 4 factorial, but based on this, the way we worked out the branch and bound tree, we have implicitly evaluated the remaining, and we have said that the remaining cannot give a solution which is better than 270. So, it is an implicit enumeration kind of an algorithm, but in the very worst case we may have to evaluate all the n factorial which are there. So, this is how the branch and bound algorithm works for solving the make span minimization problem in the flow shop. Another thing that we could have done to cut down the computation is this. Somewhere here, when we fixed 2 jobs J4 and J1, we evaluated the lower bound and we proceeded. Here when we fixed 3 jobs, we said there is only one vacant position, so the 4th job will automatically come there, and therefore we got a feasible solution here. In branch and bound algorithms, it is customary to actually right here evaluate the feasible solution, because when we fix these 2, there are only 2 more positions remaining with 2 more jobs remaining, and they can be filled only in 2 ways. So, right here we could have said this will give rise to 2 feasible solutions, which is J4, J1, J2, J3, J4, J1, J3, J2, which means right here we could have evaluated this without doing this and without doing this 266. So, that way you can speed up the branch and bound algorithm. When you have only 2 more positions remaining, you do not evaluate the lower bound, instead you fill it in 2 ways and evaluate 2 feasible solutions. So, this is how the branch and bound algorithm works in order to minimize the make span. This can be extended to a general n job m machine based on the idea. We had 3 machines, so we calculated 3 lower bounds and chose the best. If you have m machines, you will choose m such calculations for every node and choose the lower bound. Now, in case we obviously we understand that the branch and bound algorithm is time consuming, and as the problem size increases, there are times the branch and bound algorithm is unable to give the optimum solution within a reasonable computational effort. So, in such cases what do we do is the next question that we have to address. We will address that question in the next lecture.